In this segment, we're going to talk about operationalizing value with attributes. The reason for doing so is so we can develop quantitative representations of what our stakeholders might care about for our systems, allowing us to use model-based approaches for predicting good alternative outcomes. Now, what is an attribute? An attribute is a decision-maker perceived metric that measures how well a decision-maker defined objective is met. A decision-maker is a special category of stakeholder who has significant influence or control over driving needs or resources for a system. Satisfying our decision-makers increases the likelihood that a system is made, but we must be careful to not neglect all of our general stakeholders. A value metric is a means for quantitatively converting attributes of a design or alternative into a measure of preference. It's quantitative, although often dimensionless, and could be relative. It aids decision makers in choosing between disparate alternatives. There are different types of measures of value, ranging from functional requirements, which may be binarily satisfied. For example, do I meet a particular threshold value for miles per gallon or range? Or they can move on to single measures of functionality. For example, what's the degree to which I have miles per gallon? What is my range? Where there's a range of acceptance across this measure of functionality. Next, we have single attribute utility, which is an example of a value model that quantitatively transforms degree of satisfaction across a range of an attribute. Next is multi-attribute utility, which is a quantitative model that aggregates degree of satisfaction across a set of different attributes. Now, these are progressively more difficult to use and quantify, but potentially more useful in providing nuanced understanding of how stakeholders and decision makers specifically value different alternatives. Now, it's important to keep in mind that attributes themselves should be defined by the actual decision makers. These characteristics ensure that a decision maker understands what the metric means, that these attributes actually have ranges which more accurately reflect degree of satisfaction across performance. It has the added benefit of allowing us eventually to open up the trade space and consider broader alternatives that may not meet every threshold exactly the same. A set of attributes typically contains 3 to 7 elements, which reflects the reality of our own bounded rationality, our ability to think about simultaneous concepts. This may not always be possible, however, and we can use the concept of value hierarchies to decompose our value proposition into smaller sets. Practically speaking, you'll probably have to iterate with your decision makers to come up with a good set of attributes. The way that I like to think about it is to get our decision makers thinking solution neutral and thinking about the criteria they actually care about. I use the construct of a black box. Imagine you have a black box, do not think about your system, but this black box that delivers some sort of performance. What are those characteristics of performance that you actually care about? It's important that decision makers focus on what they know about, which is their value model, and not think about specifying form-specific solutions. Now, a set of attributes should be complete, operational, decomposable, non-redundant, minimal, and perceived independent. This last piece, perceived independent, helps in the elicitation process. It's important to recognize that perceived independent is not the same as actually independent. As an example, consider a satellite system where I have an imaging mission. The revisit time, or the time between revisits of a particular point of the globe, and resolution are functionally related to each other via physics. The design of an orbit determines how quickly a satellite passes overhead and therefore how quickly it revisits a spot, and its altitude, how high it is above the ground, determines the resolution. The speed of a satellite and its altitude are fundamentally related. Now, from a decision maker point of view, these two attributes of revisit time and resolution could be perceived independent, especially when they're thinking just about the data that's coming out of a black box. Another example, imagine a satellite radar system whose value proposition is to provide 24-hour, all-weather, on-demand visibility and tracking over things that can be observed on the ground. This particular system has 3 high-level missions, a tracking, an imaging, and a programmatics that correspond to 3 different decision makers. Each of these 3 decision makers were interviewed, and 4 to 6 attributes were elicited. An example tracking attribute was target track life, whose units was minutes, and acceptance range went from 0 to 30, where 0 minutes was the least acceptable, and 30 minutes was the most desirable. For the imaging mission, we had resolution measured in meters, where 100 meters was the least acceptable and 0.01 meters was most desirable. And then for programmatics, we had deviation from cost measured in percentage, where 200% was the least acceptable and 0 was the most desirable. By having these ranges, we allow different alternatives to provide different degrees of value to our decision makers. In my prior example, I talked about a single attribute utility as a quantitative model representing degree of satisfaction across the range of a single attribute. At the minimum acceptable level of an attribute, utility function is defined as providing zero utility. If I do worse than my minimum acceptable value, then I do not deliver acceptable utility, and that alternative is deemed as infeasible. If I perform better than my most desirable level, then the single attribute utility function returns a 1, and I get no extra cookies for doing better than my most desirable level. I reach saturation. In between, in that acceptance range, a single attribute utility function just has to be monotonic, going from 0 to 1. I can have a desire for higher is better or lower is better. Moving on to a multi-attribute utility function, which is the aggregation across the set, we use a Kini-Rifa multi-attribute utility function in our example. These take single attribute utility functions along with weightings to aggregate together into a single measure of goodness across our attribute set. The benefit of using a multi-attribute utility function is that it's transparent and traceable and provides a single metric for evaluating our alternatives. We do not lose any information, however, as we are evaluating our attributes and calculating these utilities in a transparent way, so we could always dive back into the details later.